amines and amines. Well, this is the final section of chapter 1. So here, well, amines. This sounds like a word that I think we are all familiar with. If you have ever been to a public bathroom, usually there is going to be a smell of ammonia in the air, which is a breakdown of urea, which is the nitrogenous waste product that humans secrete. Now, ammonia is not technically considered an amine, even though it behaves in much the same way, much the same reactions, and, well, amines technically have to contain alkyl groups. So, if we have a primary amine, then that means H2N, R. Secondary, HN, and then 2 R groups. And tertiary, there's going to be 3. Now, obviously, because nitrogen can only form 3 bonds, unlike carbon, there are no quaternary amines. Because, well, you can have a quaternary carbon, but you can't have a quaternary nitrogen. At least not without coordinate bonding, which is another whole kettle of fish that we'll get into some other time. Now, what happens, do you think, when we get 0 degree? Well, when we get 0 degrees, that means it has to be ammonia. So, we don't call this a 0th degree, or, well, whatever the choice of primary, secondary, tertiary, and what would be under primary. Well, we don't care. But the point is, we don't call this a 0th order amine, because it's not an amine technically. This is just ammonia. Now, ammonia is used to make amines, but we'll get to that in a moment. So when we name amines, well, here this shows how an amine might be named. We notice that here we relied on the benzene ring to provide the base name, which means, so benzene, and for 1-hydroxy-2-methylamine ethyl, methylamino ethyl. So we see that the amine side chain, because it begins with an alkyl, well, we see that very clearly the 1,2 diol takes priority over this one. So 1, 2, and then 4th, well, it's methylamino ethyl, which means that first we have 2 carbons, ethyl, and then we have amino group and methyl. So methyl, this is methylamino. So 4, 1-hydroxy-2-methylamino. Okay, so this is 2. Yeah, that makes sense because it's 1, 2, and then here we have a 1-hydroxy. So this is epinephrine. Why is it called epinephrine instead of the more commonly used term adrenaline? Well, they actually mean the exact same thing. Nephron, or nephritic, or something with a nephra base, is the word for kidney in some ancient language. Renal is another word for kidney. So adrenal is above kidney. And epinephra is, well, you've probably heard of epicenter or epi whatever. So it means generally outside. Well, clearly the adrenal glands are outside the kidneys. So, now I'm not very well versed in the ancient languages, so that's just a educated guess. Of course, nephra and renal do in fact mean kidney because we have kidney nephrons. So they do mean nephrons, and, well, that actually doesn't matter here because we're actually dealing with amines. We point out that the urea molecule is not an amine due to the bond pattern. Now, it has an aromatic ring, it's an alcohol, and it is an amine. It is a what degree amine? This is a secondary amine because it has 2 carbons attached to it. Now, we don't concern ourselves with the R for now because this is for optical activity, which is a stereochemistry matter. So this thing will turn light to the right when light passes through it. Now, in the naming of amines, the IUPAC names and common names can seem very similar. For example, methanamine is the IUPAC name. The common name is methylamine. The common name just names the methyl group as a substituent on ammonia, pretty much. So, technically speaking, we should name the amine as a substituent on methane. Now, as per the epinephrine example, though, you can accept quite a number of things by IUPAC. Now, methylamine, as shown above, is technically a substituent, and it means this substituent. So whatever is here, this is a substituent called methylamine. What would be ethylamine then? Ethylamine would be this. And what happens then? Well, technically ethylamino, but most people will understand what you're saying even if you happen to mix it up, as many chemists often do. So, ethylamino, methylamino, these are substituent groups. If you have ethanamine, that means it's not a substituent and it's just this. Now, amines with substituents are named with this being the first carbon and this being the second carbon, and so on. They are used using the longest chain. So, for example, if your nitrogen is attached to, say, this, and this way, then that would be N-ethyl. Remember, this should go in alphabetical order. N-methyl. And what is this? 1, 2, 3, 4, 5. So, pentanamine. Now, if you had a substituent over here, that would be, instead of N-ethyl, N-methyl, it would also include a 3 whatever in appropriate alphabetical position. Now, you may have seen bottles that are labeled, say, diethylamine or trimethylamine or similar. But technically speaking, they should be named with all the other alkyl substituents as well, substituents on the nitrogen instead of trimethylamine. Now, yes, I do realize that this is much shorter than this, which is why it is still commonly printed on chemical bottles and is more or less accepted by IUPAC simply due to being old enough and convenient enough. For example, aniline, instead of benzamine, we have aniline because, well, old name. You'll find that a lot of things in chemistry are grandfathered in. For example, what are you mostly? What am I? Water, mostly. So that is clearly an IUPAC name that has been grandfathered in. So, aniline is an amine group on benzene, so this replaces one of the hydrogens with an NH2. Now, what about N-phenylalanine? Well, N-phenylalanine is aniline. Now, why is it that most chemists prefer to draw these skeletal structures? It's because they don't want to accidentally label, oh, aniline, NH2, and then have to erase the 2 to make room for, here, another phenyl group. You can label the H's at the end if you really want to, or if they're involved in some reaction, but often don't even bother. Of course, on say COOH or a functional group, you will of course have to label the H's. And if you decide this amine can qualify as a functional group here, i.e. it is important to the function of the molecule, you can feel free to include it. It is convention that you always include H's when they're attached to oxygen. But on nitrogen, you will often find that it is somewhat optional to label H's, unless they are terminal, like say a long chain ends with an NH2. Occasionally though, you will see ends in the middle of a molecule without H's labeled. But as long as they aren't specifically presented to have a charge, then that's still fine. So say N plus, wait a second, that has to be NH2 plus, because it has to pick up another proton, just like ammonia picks up protons, because as we should know, ammonia is basic. And amine groups tend to also be basic. So, ethene attached to an amino group. Ethene is double bond. Attached to an amino group. NH, how many? Well, we know that ammonia is 3 hydrogens, so we replace 1, and that leaves us with 2. So this is this structure, and it is named, instead of ethanamine, we have ethenamine. And then there's the option of course, ethynamine, which would be triple bond, and this would be straight. N-butyl-3-ethyl-aniline. Now, we start a new column. This is a method that is generally recognized as okay, to use a dashed line to start a new column. When you are running low on space, and this is very common in contests, you will often find yourself having to start new columns to show all your work within the space allotted, even though they sometimes allot you whole pages for problems. So, N-butyl-3-ethyl-aniline. So we start with aniline. N. And N-butyl. And 3-ethyl-aniline. So if we know it's aniline, it has the number starting with the N, right? Because aniline is treated as a core molecule. So 1, 2, 3. In either direction is fine. They are still the same thing. So 3-ethyl-aniline. That means this. All right. So we know that ammonia has a fairly high melting and boiling point for its particular atomic mass, well, molecular mass. So that means that it has hydrogen bonding. Well, N is considerably more electronegative than hydrogen, so it undergoes hydrogen bonding because of the large dipoles that are generated in each bond. So what does that mean? Well, amines lower what? Lower volatility than expected. So in other words, lower volatility means higher melting point and boiling point. You will sometimes see this term used instead of higher boiling point. This is just to make sure that you can recognize it. Now, what else can we think of? Well, we know that ammonia is basic. It can pick up protons because of nitrogen's lone pair, forming a coordinate bond. So amines have a lone pair. That means they can also do this. So basic, to some degree or another. And what about other than that? Well, there's also, let's think about this. We know that if you have a polar functional group of some type, it's relatively more soluble than, say, the alkane or alkene or whatever alkyl group you started with. Now, as the alkyl group gets bigger, the effect is diluted. So, with smaller alkyl groups. Now there's a difference here compared to dealing with alcohols. With alcohols, you will find that tertiary alcohols, which are attached to a carbon that's attached to 3 other carbons, are more soluble than primary alcohols for the same number of carbons. Why? It's because, unlike nitrogen here, we aren't using the polar part as part of the main chain. That is very important. It means the polar part stays just as polar no matter what you tack onto the other side. And so as the more compact the other side, the more polar the overall molecule can be. And the smaller the hydrophobic part sticks out. But with amines, if you tie it up so that, say, trimethylamine, that is not going to be as soluble in water as you might think. So, because, well, first of all, it's symmetric, which is bad. Being symmetric is very, very bad for solubility. Why? Because a symmetric molecule doesn't have an overall polarity, unless it ionizes, which trimethylamine admittedly can do. So it's a little bit more complicated than with alcohols when it comes to solubility. But in general, smaller alkyl groups is still more soluble. So, amines. We don't need to concern ourselves too much with the solubility rules for amines yet. For amides, what are amides? Well, amine, amide sounds related, right? Well, yes, they are related. Essentially, the amide is the nitrogen counterpart to an ester. Now, we note that this is the most common form you will see amide written in. Why? Because the closest amides that we personally experience are all of this form. Well, almost all of this form. Proline is an exception, but